Hi everyone, in this video we're going to go over the solutions to worksheet of the week 3. Now first we want to differentiate this statement here, y equals x to the minus 1/3 plus the square root of x times x plus 1. So there's two ways that you can go about doing this. So number one is multiply all this and consolidate before making a derivative. So if you multiply x by this is like x to the 3/3 times x to the minus 1/3. This is going to give me x to the 2/3. Now this x by this x to the 1/2, because remember square root of x is x to the 1/2. Then x by square root of x is going to be x to the 3/2. And now we multiply the 1. So it will be plus x to the minus 1/3 plus x to the 1/2, that is the square root of x. Now, once that we get that, then notice that we can just simply differentiate here. So y prime will be 2/3 x to the 2/3 minus 1, which will be minus 1/3, plus 3/2 x to the 1/2. If I subtract 1 from here, 3/2 minus 2/2, which is 1, will be 1/2. Then minus 1/3, x to the minus 4/3, and 1/2 x to the minus 1/2. Okay, so one of the challenges that this exercise has is that you actually have to subtract 1 from each of the powers, and you got to be careful doing the rational differences in there. Okay, so be careful when you're doing these calculations in this way with rational powers. Just make sure that you're getting the right power here. Okay, so that's way number one. Way number two is we're gonna use product rule. So for product rule, remember if we have y equals f times g, then y prime is going to be f prime times g plus f g prime. Okay, so if this is f and this is g, then y prime is going to be what? F prime is going to be minus 1/3 x to the minus 4/3. This is the derivative of x to the minus 1/3, and 1/2 x to the minus 1/2, and that's just the derivative of f, and then we multiply by g, which is x plus 1. Now in the next one we add f, which is x to the minus 1/3 plus x to the 1/2, right, and the derivative of g, which is 1. So depending on whatever you think, this might be an easier approach because you have to do less powers. But you gotta state very clearly the product rule. Okay. Now, exercise number 2 goes by using the definition of derivative. Let's prove that if f of x is b to the x, where b is bigger than 0, then f prime is gonna be b to the x times this limit. And this is just consequence of the definition, because if we have limit when h goes to 0 of f of x plus h minus f of x over h, then what is this? This is the limit when h goes to 0 of this is b to the power of x plus h minus b to the x over h. Remember that when we're doing f of x plus h, we're just replacing x by x plus h. Now, what happens here is that notice that b to the x is a common factor. So I can actually go ahead and say, well, this is b to the x factor of b to the h minus 1 over h. Now, notice in this limit, this b to the x really doesn't matter. This has nothing to do with h, so I can just plug it outside or put it outside of the limit. And this is where we get our result. We wanted to prove that f prime, that by definition is this, was this. So we just proved now that that was true. Now we want to explain why that means that if f prime is e to the x when f of x is e to the x. So well, if b is equals e, which is what essentially is happening, then f prime is e to the x limit when h goes to 0 of e to the h minus 1 over h. And then there are multiple ways that you can go about doing this, but this is essentially a 0 over 0 situation. So this limit is going to be 1. Notice that e to the 0 is 1, 1 minus 1 is 0, and in the bottom we also have that this is 0. Okay? So what's going to happen here is that this limit, which we can do by multiple means, this limit is actually 1. Okay? And so the result of this is e to the x. Now, in exercise number 3, we want to find the derivative of y, being this 2x cubed plus cube root of x plus x divided by x cubed. Again, this is two ways of doing this one. The first one is, let's rewrite y as 2 plus x to the 1/3 over x cubed plus x over x cubed, or this is just 2, and this is plus x to the, and 3 will be 9 over 3rd, so this will be minus a over 3, simplifying, and this will be x to the minus 2 when we're simplifying. And so again, the derivative here will be 0 minus a over 3 x to the minus 11 over 3, and then minus 2 x to the minus 3. That will be the derivative. This is, again, if we're just using the method of simplifying what the function is before doing anything. The second method that I can use is the quotient rule. Okay, so in this case, if y is f divided by g, remember that y prime is f prime times g minus f times g prime over g squared. And so with that method, then we have that y prime is going to be what? F is this stop over here, and the derivative of that one will be 6x squared plus, and this is x to the 1/3, so this will be 1/3 x to the minus 2/3 plus 1. That's f prime. Now g continues to be x cubed, and then f, now I just write the same thing. And then multiply by g prime, which is 3x squared, divided by x cubed power to the 2. Now, you might be wondering, is this really the same as this? And yes, this is going to be exactly this, but you will have to simplify a lot to get from here to here. So we're not going to do that here. I'm just showcasing that you have two different methods that you can use to actually reach that answer. Now, exercise number 4 says biologists have proposed a cubic polynomial to model the length of L, where L is the length L of Alaskan rockfish as a certain HA, and L is given by this function here, this cubic function, where L is measured in inches and A is measured in years. We want to calculate what the LDA is in A equals 12 and make an interpretation of this. So now the LDA is just essentially the derivative, right? So it's L prime. So if we multiply by this, and let me just have something to multiply that particular value, then this is what we're gonna get. So this is 3 times 0.0155, which is going to be 0.0465 a squared, and then minus, and then we're going to multiply this number by 2. 0.372 times 2 is going to be 0.7444 a, and then plus 3.95, and that's it. And this is the derivative of this. Now, if we're plugging this when it's equals to a, then let me just use Desmos calculator for that. Okay, so let's plug in there. Y is equals to 0.0465 a squared and minus 0.744 a plus 3.95. And so now we have our function in there. I'm going to call this f of a. Okay, and now I'm going to calculate what f of 12 is. So it turns out that f of 12 is 1.718. So if I want to calculate that here, if I want to just find out what this value is equals in 12, I just need to plug in 12. And that's exactly what I did with the result that I got. You plug in 12 in each of these things. So here, 12 squared minus 0.744, 12 plus 3.95. I just did it with a calculator, but you perfectly can do this by hand. Okay? Or when you're doing it here, you can just do it with a calculator. In an exam, you won't be able to do it, but in an exam, you probably won't get this complicated numbers. Okay, so this is 1.718. And just gotta remember that this is a rate of change. So L is measured in inches, and A is measured in years. So this is 1.718 inches per year. And so the interpretation of this is the length of an Alaskan rockfish is increasing, and it's increasing because it's positive. If the rate of change, which is the derivative, is increasing because it's positive, it's increasing by 1.718 inches per year when, or if you want, at 12 years, because that's when A is equals 12. So this is one way of interpreting this. You can also start with at 12 years, the length of the Alaskan rockfish is increasing by 1.718 inches per year. In that, you can kind of change a little bit where you're going to allocate this part. But it's always important that you say when, what, how. Okay? Now, for exercise number 5, we want to find the equation that is both tangent to the graph of y equals x to the 4 plus 1 and parallel to this line. So, thing is, says find an equation that is both tangent to this. Okay, so if we want that is tangent to this, we're going to use the derivative at a certain point. Okay, so we're going to get the derivative, y equals 4x to the cube. Okay? But now, also, we want this to be parallel to the line 32 x minus y equals 15. So let me rearrange this this line. This is 32x minus 15 is equals y. So if this is the line, it means that the slope is 32. If I want that a line is parallel, then this must have the same line. It must have the same amount on the slope. So this slope must be 32. So this means that then 32 gotta be equals to 4x cubed. So this means that 8 gotta be x cubed. So this means that x gotta be 2. Okay? And so we just found the x. We just found the x. Now f of 2, which is the value, will be 2 to the 4 plus 1. So it will be 17. So now the equation of the line will be given by y minus y0 equals m x minus x0. And always remember that the y0 is just the f of the point. So in this case it will be f of 2. The m will be f prime of 2. And here we're going to have x minus 2 because we found that the point was 2. Now we also know that f prime of 2 gotta be 32. So at this point we can just plug the values that we know that we're supposed to get. And this is going to be the equation of the line that is both tangent to this graph and the point x equals 2, of course, but it's going to be parallel to the line 32x minus y equals 15. In this next exercise, we have to evaluate the limit when x goes to 1 of x to the 1000 minus 1 over x minus 1. To solve this limit, you gotta recognize that what we really have is here is a situation of the form limit when x goes to 1 of a certain f of x minus f of 1 over x minus 1. If we identify this, then this means that what we're really getting is f prime of 1. This is what this limit is. Who's the function? Well, the function is f of x equals x to the 1000. And so that also means that f of 1 is just going to be 1 to the 1000 and it's 1. So that means that this is correct. So this is like f of x, f of 1 over x minus 1. So if this limit is going to be equals to f prime of 1, I just need to find out who f prime is first. But f prime is just a power. So this is 1000, x to the 999. And so when I plug in 1, f prime of 1 is just going to be 1000. And that's it. So the f prime of 1 here will be 1000. And this is a way to use the derivative to get the value of a specific limit. Now, for exercise 7, consider the following graphs. We want to be considering f times g, and if possible to calculate h prime of 0, h prime of 1, and the lateral limits here. Notice that to be able to consider any of the derivatives at a certain point, we can consider the slopes of the tangent line. But because these graphs here are specifically lines, then the only thing that we need is the slope, and that's going to give me the derivative of those points. So notice that we have an issue when we're approaching 0 with f, because by one side we have a different slope. We have the slope, this slope seems to be minus 2. And from this slope here, and this slope here seems to be 1/2, or like around 1/2. So it means that the slopes are not going to coincide, and so that means that f prime of 0 does not exist. And because f prime of 0 does not exist, then h prime of 0 does not exist, because h prime of 0 is defined in terms of f and g. So that do not exist. Now, h prime of 1 is a different matter, because notice that h prime of 1 can be seen as s prime of 1 and times g of 1 plus f of 1 times g prime of 1. So by product rule, of course. So f prime of 1 is this like 1/2 over here. This rule over here is like around 1/2. You might want to calculate exactly what the slope of this line is, but we can say now that it's 1/2 by now. And how did you calculate the slope? Well, you can take 2 points. In 0 is 0, and in 3 is 2. So let's actually calculate the slope instead. So when x is equals 3, then we have this -2, and then minus, and then when it's 0 is 0. So it's actually -2/3. That's the slope of these 2 points. It's -2 and 0, so it's actually -2/3 over here. And g of 1 is -1. And then plus f of 1 seems to be 1/2, according to this, -1/2, sorry. And g prime of 1 is the derivative of the slope in here. But g prime of 1 seems like it has issues as well. It seems like it does not exist over here. And so that means that because it does not exist in here, then h prime of 1 is not going to exist. Notice that the slopes that are approaching are different. This slope is different from this. This is a negative. This is a positive slope, so the limit is not going to exist. So in none of these cases it did exist for h prime of 0 or h prime of 1. Now for the limit, we're really considering the limit when h goes to 0 by the right of f of h minus f of 0 over h minus 0. So this is really like we're considering kind of like f prime at 0, but by the right side. So we can see here that the slope of this is 2. So this is the slope of this line. When we're approaching by this side is 2, and by when we are approaching by this side, it's -2/3. So because this is the right side, then we can say that this is -2/3. This is -2/3. That's the approach to 0 from the right. Okay. Now, exercise 8 says, find the equation of tangent lines to the graph of this, which are parallel to the line y equals 1/3 x plus 2. So from this, we know that because it's parallel, the slope to the tangent line gotta be 1/3. This is what gotta be the slope. So we don't know yet when that's going to happen, but this gotta be equals to the derivative of this. So we find what y prime is. So y prime here is the derivative of x minus 1, which is 1, times x plus 2, minus x minus 1 times the derivative of x plus 2, which is 1, over x plus 2 squared. And so this is x plus 2 minus x plus 1 over x plus 2 squared. And then this is 3 over x plus 2 squared. This is what the derivative for this is going to be. Now, if that derivative, this is going to be the slope at some point, I'm going to call this m2. So that means that 1/3 gotta be equals to 3 over x plus 2 squared. And so we can find out what is the x that's going to give me that. This is x plus 2 squared equals 9. And if I take a square root on both sides, x plus 2 is going to give me plus or minus 3. And so this means that this is going to be minus 2 plus or minus 3. And so this means that I have two options. Either x is equals minus 5 or x is going to be equals to 1. Okay. And now, so these are two possible points where this is going to occur, where this line has a 1/3. And so for each of this, we're going to have one equation. So we gotta find out what is y minus f of minus 5 equals 1/3 of x minus 5, and we gotta find out what is y equals minus f of 1 equals 1/3 x minus 1. This will be the two equations. Now I need to plug in this equation 4, 5, and for 1. So if I plug in 1 here, notice that I'm going to get a 0. And so this means that the one below is just going to be 1/3 of x minus 1. And if I plug in minus 5, notice that this is going to be minus 5 minus 1 is minus 6. And minus 6 over minus 3 is 2. So y minus 2 equals 1/3 of x minus 5. And this will be the two equations of the line that are obtained from this. All right. Now, the following exercise is about calculating the derivative of the following functions. Some of them are going to be chain rules, some of them are going to be product rules, and some of them are going to be a combination. So in this first exercise, we have a chain rule situation. We have secant of x plus 1, and we can see this as power to the 1/2 since this is square root. And so if this is y, then y prime will be 1/2 secant of x plus 1 to the minus 1/2. Secant by tangent of x, which is the derivative of secant. Now, also, y, we have that y equals cosine squared times e to the 3x. This is both a product rule and a chain rule. If we have that this is the function f and this is the function g, then y prime will be f prime times g plus f times g prime, right? And so this f prime will be minus sine compose x squared times the derivative of x squared, which is 2x, and this is just f prime, then multiplied by e to the 3x plus cosine of x squared times the derivative of e to the 3x, which is 3e to the 3x. Remember, it will be the same thing. E to the 3x, the derivative of the exponential is the same, but because we have this 3 here, then we have an extra 3 coming down. So this will be the derivative of that particular function. Now, over here we have this, and these are two ways of doing this. You can either do it by quotient rule, or you can simply just put this on the top. This is 3x to the 4 plus 2 power to the minus 2. In my opinion, this is the simplest way of doing this. Just put upstairs and put a negative sign. And so y prime will be here minus 2, 3x to the 4 plus 2 to the minus 3 times, and then by chain rule, this is 12x to the 3. Now, this is just the way of doing it by doing the chain rule. If you're gonna do it by thinking of it as a quotient rule, then you gotta rearrange things a little bit more. So if this is h, let's say f over g, then h prime will be f prime, which will be 0 by 3x to the 4 plus 2 squared, right? Then minus, and then this one without derivative, and then the derivative of this one, which will be 2, 3x to the 4 plus 2 power to the 1. And then, of course, there's a chain rule in there as well. So this will be 12x to the 3. And then, of course, everything divided by 3x to the 4 plus 2. A square, so to the 4th. And so notice that when you simplify this out, you're going to get the same result. Now, number 4 is tangent of e to the x cubed plus 1. So again, this is this type of function, tangent e to the x cubed plus 1. So there is a double chain rule in there. When you take the derivative, the first derivative that is going to come into play is the tangent, which is going to be secant square. So it's going to be secant square from e to the x cubed plus 1. And then times e to the x cubed plus 1. Right? And this plus 1 is actually on the top. So you got to be careful here. So the derivative of e to the x cubed plus 1 is actually going to be e to the x cubed plus 1. But then we have a further chain rule, which is the chain rule of x cubed plus 1, which is going to be 3x squared. Okay? So this is finally the last chain rule that we can get out of here. And this is the derivative of this complicated function. Now finally, for exercise 10 over here, we're going to go with analyzing what some of the derivatives and some of the values are going to be. Notice that we start with f composed g of 1. So to find out this, I got to find out first who is g of 1. So g of 1 is actually 3. So this is just f of 3. And then I can find out who f of 3 is. F of 3 is 1. So that's the end result of this. Now, if we are considering that y is equals f of x and x is equals g of t, when we're considering y, we're considering really the function f of g of t. So if we're doing here the y dt, this is the chain rule. And they're asking me for the chain rule and t is equals 2. So this means that they're asking me for f prime of g of 2 times g prime of 2. That's what the chain rule in there means. Again, we first find what is inside. G of 2 is 4. So notice that this is going to be f prime of 4 times g prime of 2. Now, but what is this f prime and this g prime? Notice that we have lines. And so when we have lines, the slopes means the derivative. So if I want to get f prime of 1 from this function depicting f, what I need is the slope of the line that's crossing 4. And notice that this is something that we can get from 2 points. So for example, we can pick this point. When the function is at x equals 3, it gives me 1. And when the function is at 5, it gives me 4. So I get 4 minus 1, the difference on the y's, over the difference on the x. So this is 4 minus 1, 5 minus 3 is 2, so 3 halves. So this means that f prime of 4 has a slopes 3 halves. Now g prime of 2. G prime of 2 is working with this slope, the slope of this line. And so notice that in 1, this is 3. So I can go, well, in 1, this is 3. And I can also go ahead with in 2 is 4. And so this is 4 minus 3 over 2 minus 1. This is just 1 over 1. This is just 1. So this means that g prime of 2 is a slope 1. And this is just going to give me 3 halves. Now, same thing for the example of t is equals 4. We have f prime of g of 4 times g prime of 4. Now, g of 4, notice that is going with this number, 3. So this is the same that f prime of 3 times g prime of 4. Let's see what f prime of 3 is. Notice that f prime of 3 is not defined because there's a peak. So the derivative does not exist here. And because one of these two derivatives does not exist, then overall this does not exist. So now exercise 11 is pretty much just reminding you of what the derivative of diverse functions are going to be. And you're going to need to memorize this for quizzes and exams. So it's always a good idea to have these rules and these particular functions clear. So for example, the first derivative of 0 is just going to be 0. It's a constant, and the derivative of any constant is 0. That's why 1 and c are also going to be 0. The derivative of x is going to be 1. Is 1 power, is x to the 1. So if functions like a normal power, we put down the exponent and we subtract 1. And so when we have just x to the 1 is 1 down, x to the 0, and that's essentially going to be 1 again. In general, the power is n, and then you put down the n, and then subtract 1 from the exponent, and that's going to function regardless if this is an integer, if n is an integer, or if it's a rational function, rational exponent, like for example x to the 1/2. The exponential is always itself, so if the derivative of the exponential is the exponential again, and if we have something extra here, then that might multiply. So for example, in the case of a to the x, this is the basis of number here, is the number a, and so we're gonna do the exponential of e to the x is e to the x, and then we're gonna multiply for log of a to the x times log of a. That's the derivative of this particular exponential, and the exponential base e is just e to the x. Now the formulas for the subtraction and the sum are going to be in terms of the same addition or subtraction. So we have the derivative of the sum is just going to be the sum of the derivatives as well, and in the subtractions functions in the same way. If we have a constant multiplying a function, that constant is going to go out, and we're just going to have the derivative of the function. And if we have a product of two functions, then we're going to use the product rule to summarize how the derivative of that product is going to be. With the quotient, it depends on how you're doing it. For example, here we have g times f, so in this case g over f, so in this case is going to be g prime times f minus g f prime divided f square. But this is because we have f below. Sometimes we have f over g, and so we got to be careful of the order of those terms. Now number 12 here is just a reminder of the chain rule. The derivative of f composed g is just going to be f prime composed in g times g prime. Derivative of sine is cosine. Derivative of cosine is minus sine. Derivative of tangent is secant square. Derivative of secant is secant by tangent. Derivative of cosecant is minus cosecant by cotangent, and derivative of cotangent is minus cosecant square. The derivative of the log is 1 over x, natural log of x. And if we take the derivative of the log of a function, this is a chain rule, so it's going to be 1 over f of x times f prime of x. Okay. The derivative of the log of base a of x is going to be 1 over x times 1 over log of a. The derivative of sine to the minus 1 is going to be 1 over 1 minus x squared. And the derivative of the cosine inverse is going to be the same, but the only change is going to be that this has a minus 1 in here. The derivative of tangent to the minus 1 is going to be 1 over 1 plus x squared. And the derivative of the cotangent is the same thing, but with the minus. And the derivative of the secant is going to be 1 over x squared, the square root of x squared minus 1. And the derivative of secant to the minus 1, it's going to be minus 1 over x squared. Sorry, this is not x squared, but absolute value of x. Actually, it's the other way around. The minus is for cosecant, not for secant. Okay, now exercise 12 is about implicit differentiation. We have tangent of x equals y squared cosine of x plus xy minus pi. So the derivative of this is going to be secant squared. From tangent is going to be secant squared. Here we have a product rule. This is going to be the derivative of y squared 2y. But because this is a y function of x, is going to be a chain rule here, and this is going to be times y prime multiplied by cosine of x plus, and then now y squared times the derivative of cosine, which is minus sine of x. And then we have the derivative here of x times y. Derivative of x is 1, so 1 times y plus x times 1 times y prime. And then the derivative of pi is going to be 0. Reorganizing this a little bit, we have that secant square of x is equals to, and then now we're going to get together everything that has a y prime multiplying. So this is going to be 2y cosine of x plus x, and all this is times y prime. And then all the other terms that have no y prime, so for example here we have y, and then we have this and this one here, minus y squared sine of x. And notice that that accounts for every single one of those terms. We have this one, we have this one, and then we have this piece and this piece. Okay. Now we move anything that has nothing to do with y prime to the other side. So we have secant square of x minus y plus y squared sine of x, and then we divide that to y cosine of x plus x, and that's going to be equals to y prime. But remember that another way of calling y prime is the y dx. Okay, so that's the derivative using implicit differentiation here. Now for exercise 13, we have this x to the 2x times square root of 3x plus 1. And this is something that we can do much more easier if we use logarithmic differentiation. So if we have this, we apply log on both sides. And then by properties of the log, this log of product is going to be equals to the log of the sum. And then now we use power properties of the log, and this is this. So simply, if we take derivative now in here, this is going to be 1 over y times y prime. And if we take derivative here, this is going to be 2 log of x plus 2x times 1 over x for this. And then with this derivative is going to be 1/2, and the derivative of log of 1 over 3x plus 1 is 1 over 3x plus 1 times 3. And now we can simplify a bit, and this is going to be y prime is going to be equals to 2 log of x plus, and then notice that this x can cancel with this, plus 2. And then over here we can simplify this a bit and write it as 3/2 over 3x plus 1. And then we're going to be multiplying here by y. But remember that y is really this. So we can see this now as 2 log of x plus 2 plus 3/2 of 3x plus 1. And then times x to the 2x, the square root of 3x plus 1. And that's the end result with this logarithmic derivative. Now, on exercise 14, we're trying to differentiate this arctangent from this arcsine of 3x squared. So this is an insane chain rule here. And we have that dy dx, or y prime, is just going to be 1 over 1 plus. And then normally this would be, because it's our tangent, it will be whatever is inside. So arcsine 3x squared x squared. So the derivative of arctangent, which is 1 over 1 plus x squared, composed on the arcsine of 3x squared. And then by chain rule, now we do the derivative of the arcsine, which is going to be 1 over square root of 1 minus, and then whatever is inside, which is 3x squared, x squared. But then by chain rule again of the derivative of 3x squared, which is going to be 6x. And so this is the whole derivative for this function. Now, exercise 15 is an example of related rates. We have that a light is attached to the top of a 10-foot pole. A light is attached to the top of a 15-foot pole, and a 6-foot tall person is walking away from the light. So we have a situation where we have a pole, and then the light is over here, and there's a person that is walking down over here, and this person is 6 foot, right, and is walking away from the light to a certain speed. This is going to create a shadow. So the shadow that is projecting is here. And so we want to know what is the rate the length of the shadow is changing. Okay. So first than anything, let's search for some information. So this is a 15 pole. So let's make a triangle with the two heights. So that's the situation that is happening, but really I'm going to have this situation here where this is 15, this is 6, and this is an amount of the shadow, which is x, that I don't know how much that is, and a person that is walking away a certain amount is 5 feet per second, but this is a distance that I don't know yet, so I'm going to call it x. Okay. We want to know what's the rate of change of the shadow, so we have we don't know the information about x, but we know how the x dt is, because it says a 6-foot person is walking away from the light at a speed of 5 feet per second. So it means that the x dt is changing in 5 feet per second. So this one I know, but I want to know what is the x dt. So how fast is the length of the shadow occurring? We have some relationships here in terms of the triangles. By similarity of triangles, I have that 15 is to 6 in the same way that x plus s, so the big one, x plus s is this whole distance, is going to be to x. So we're doing similarities of triangles between the big triangle that has 15 and x plus s length, and the small triangle that has 6 and s. Okay. So from this notion here, we can probably make everything. So we have x in terms of x. So we have 15 over 6 s is equals x plus, and then I'm going to be calling this 6s over 6. So all this is in terms of 6. If I subtract this, then I'm going to have that this is 9s over 6 is equals x, or dx of x is 6 over 9x. Now this is just ds dt, but remember, if we assume that this function is in terms of t, so this is s of x of t, and so this is 6 over 9 x of t. So dx of t is going to be what? It's going to be this 6 over 9 dx dt. And then because we know that this is actually 5, then this is 6 by 5 over 9, and this is feet by second. And so this will be 30 over 9 feet per second. Okay, and so this is one of the exercise of related rates, and this concludes the exercise of week 3.